Hi, this video is going to be on points of inflection. So we've already looked at, in the previous video, we've looked at increasing and decreasing functions and then stationary points. And we found that there were two types of stationary point in the previous video, where one was a maximum, one was a minimum. There's a third type of stationary point, which is called a point of inflection. And it looks something like this. So our curve is increasing. We get to a point here where the gradient is 0. It's kind of leveled out, the gradient 0, but then it continues and it continues to increase. Before, what we were looking at, so a maximum point, for example, if we have something like that, it's increasing until we get to the turning point here where it levels out, the gradient becomes 0, and then it changes direction. And it becomes decreasing. The gradient becomes negative. A point of inflection is that it's increasing and then continues to increase after the turning point. There is no change in direction of the graph. It just continues in the same way. What does change is that it changes from convex, so convex being like this shape, to concave like this, which you probably come across in science. With like lenses, you have like a convex and a concave lens. Same using optics. But basically the line curves in one direction before your turning point, before your point of inflection, and it curves in the other direction afterwards, but it's still continuing in the same general direction. It's still increasing and continues to increase after the point of inflection. This could work the other way around. It could be like this and decreasing. So decreasing, point of inflection continues to decrease. It doesn't have to always be positive and increase a positive gradient and be increasing. What we've looked at so far, so we know that there are 3 different types of turning point or stationary point. What we need to look at next is how to identify which type it is. So whether it is a minimum, a point of inflection, or a maximum. Sorry, I'm just going to drink some water. I feel like I'm talking so much. So there's 2 ways of doing it. The first way is a bit longer and a bit more kind of what's the way to describe it? It's quite a practical way of doing it, like a intuitive way of doing it, I guess. Whereas the second way involves more differentiation. So how to tell what type of stationary point is? If it's a minimum, the gradient just before the stationary point, just before the turning point, would be negative. Then we get a gradient of 0 where the actual turning point is, and then afterwards it continues on in the positive direction. If it's a point of inflection, the gradient just before would be positive and the gradient after it would be positive. Basically the gradient is the same, because again, that could work the other way. We could have negative and negative, not just positive. Or we could have a local maximum where the gradient just before it is positive. Then we have the turning point where the gradient is 0, and then just afterwards the gradient is negative. That should say, not positive. That's what those mean. I don't know if you're used to that notation. We used to use it a lot when I was in school myself. But yeah, positive, plus for positive, and then VE for the if at the end. I don't know if I'm making any sense. But that's all that notation means. So for a maximum, it would be positive, 0, and then negative after the turning point. So we're going to go through 2 ways of deciding whether our turning points are maximum, minimum, or point of inflection. So the first way we could do it. Either way, we are going to have to differentiate first. So method 1, we've got y equals x to the power of 4 minus 32x, and we want to find whether the stationary point is a maximum, minimum, or point of inflection. So differentiate it. So dy by dx would be 4x cubed minus 30, 23, 32. At the turning point, that is equal to 0. So we want to put 4x cubed minus 32 equals 0. So 4x cubed is equal to 32. Divide that by 4 is 8, so x is 2. That's my x value. The corresponding y value, I'm going to substitute 2 into 4x cubed minus 32. You know how to do that. I'm just going to tell you the value that I get is negative 48. So my stationary point is at 2, negative 48. What I want to do is decide what the gradient is either side of that stationary point by picking a value, an x value, either side of my stationary point. So essentially what I'm going to do is substitute in to my dy by dx, because I'm looking to see what the gradient is at these points. So I'm going to choose a point slightly less than 2, so say x equals 1.9, and a point slightly above 2, so x is 2.1. And I'm going to substitute those values into my dy by dx and see if they are positive or negative, which will tell me what type of stationary point I have here. Okay, so by putting in x is 1.9, I get dy by dx, not y, dy by dx. Again, you know how to substitute. I'm not going to insult your intelligence by talking you through substituting 1.9 in. I get dy by dx is negative 4.56, so a negative gradient. When I put in x equals 2.1, dy by dx is 5.04, so that's positive. So before the turning point, my gradient is negative, then I have the turning point, and then my gradient is positive afterwards, which means that this is a minimum point. So therefore, the coordinate that I found, 2, negative 48, is a minimum point. I can't do anything today. My brain is just not working. I've had a couple of days off and it's just stopped. It doesn't know what to do anymore. There we go. So that's method 1. A bit long-winded, a lot of kind of substituting things in, potentially room for error, depending on how you substitute. If you get a negative wrong or something, do you know what I mean? Like there's lots of potential for error there. The second way is by using something we call the second derivative, which is essentially differentiating twice. So when we have a stationary point, so we know what the stationary point is, I don't know if you can hear that. My next door neighbour, someone's knocking at the door and they just knock continuously, like knock once and wait. But these people come to the door and just knock and just keep knocking until someone answers. That's not normal behaviour, right? Like that's so weird. Anyway, okay, so we know once you've identified that you have a stationary point, you know where it is, you have the coordinate of the stationary point. If you differentiate your differentiated function, so you differentiate again, which is what this is, the double dash, it means we've differentiated twice, the second derivative. If we substitute our x value into the second derivative and we get something greater than 0, then we have a minimum. If we substitute our x value in and we have something less than 0, the point is a maximum. And if it is equal to 0, it could be any, which is super helpful. So then we would have to go back and do method 1 anyway, which is why I don't just teach you the one way, because if we get to this third situation and we've differentiated twice, we've substituted in our x value and it's still equal to 0, then we're going to have to use this first method anyway. So let's have a look at doing this. It's the same question as before. So y is x to the power of 4 minus 32x. We already know where the stationary point is. We know where it's at because we've already done it. We know it's at 2, negative 48. We know when we differentiated, we got dy by dx is 4x cubed minus 32. We need to differentiate again. Now, you've seen the notation for the function. It's just a double dash. For dy by dx, it's d squared y dx squared. We used to have a strange way of saying that. I think we used to say d2y dx2. Something I can't remember how we used to say it. But that's how you write it down. D squared y over dx squared. So what we're doing is differentiating the function that has already been differentiated. So that becomes 12x squared and the 32 disappears. And then we're going to put x into that function. So when x is 2, our second derivative is 12 times 2 squared. So 12 times 4 is 48. This is positive. So our second derivative is greater than 0. Therefore, the point we've got to negative 48 is a minimum. Because if it's greater than 0, then it's a minimum. We're using the first one there. Oh, that doesn't show up very well over the black, but never mind. Yeah, but as you can see, that's a bit quicker than the first method if we actually get to a point where it gives us something either less than 0 or greater than 0 and not equal to 0. And I think that's it. That is it. There is a third video which I actually made last year on modelling problems. So basically using your techniques for differentiation in a real life context. They love these in an exam. So definitely worth watching. I will send you all 3 and the PowerPoint for you to have a go at over the break. And then when we get back, if there's questions, if there's things you're not sure of, we'll try and get through them in class together. Yeah, bearing in mind that we're going to be doing shorter Ramadan days, but it'll be fine. We can do this. Yeah, so I hope that helps. If you do have any questions in the meantime, drop me an email, send me a message on Google Classroom, and I will get to work on the integration. Again, I have some of the integration videos from last year, but I do have to make kind of the last part. I've got the first few. I need to make the last part of integration, which I'll try and do either later on today or tomorrow. So yeah, I hope you guys are enjoying the break, and see you soon.